Hello everyone and welcome to another Stat 437 lecture video. Today's lecture video is going to be a review of generalized linear models. So just like when we reviewed linear regression a few lectures ago, I'm going to be assuming that this is review for just about all of you. And so I'm going to go through it fairly quickly. I'm going to cover the topics that we're going to need from generalized linear models for this course. And so if this isn't enough detail, if you have any questions remaining after I'm through this lecture, definitely let me know and I'm happy to go into sort of more detail as you need. But again, I'm assuming you've all seen this, so this is just a refresher of what points are important for our course. So with that, we'll start by sort of asking, what are GLMs? And so if you remember from your GLM course when you last took it, there are sort of GLMs are the natural extension of linear regression to any different type of outcome, right? So linear regression relies on our outcome being a continuous variable, right? And then it takes these continuous variables and it sort of extends the concept of using a linear function to accommodate any kind of data that we might care about. And so with a GLM, the idea is that we're going to be able to work with non-normally distributed data, but also we're going to work with, count data or binary data or whatever else we might want to do. And so it's the natural extension there. And it's comprised of three main components, right? So if we're thinking about how do we specify a GLM, there are three things we have to specify in order to specify the GLM. The first is we need a random component. So typically, the way we're thinking about this random component is through the use of a distribution, and specifically an exponential family distribution. Now, I'll review briefly what exponential family distributions are momentarily, but for right now, basically what we're going to say is that we have some outcome variable that we care about. It's yi in our notation, and yi follows a distribution f of y parameterized by some parameter theta. Okay, so we first have our random component. Next, we need to specify a linear predictor, right? So we're going to call this eta I. It's equal to xi beta, and it's based on our variates of interest, right? So it's our linear predictor because we have this linear form where we take whatever covariates we care about in x, we multiply those by a parameter vector beta, and that's called our linear predictor. And the general idea with the generalized linear model is that we want to link this linear predictor to the random component. And the way that we do that is through the third component, the link function. Right? So our link function is some pre-specified function g, such that when we apply g to the conditional expectation, we get the linear predictor. Okay, so just thinking about this very briefly, if we take g to be the identity function, right, so g of x equals x, well then g of the expected value here is going to equal the expected value itself, which equals eta I, right? And so in that case, we're basically thinking of this as a standard linear regression, right? So if g is the identity function, then we don't really have g, and then we're just looking at the expectation equals eta I, which is our standard linear regression. But of course, we can specify any other function we want there. And the idea is that when we specify this function, we're then translating our expected value into a range where it is linear with respect to the variates that we care about. And then we've connected the random component to the linear predictor through this function g. So we need to specify those three components. And when you've specified those three components, we have a generalized linear model. Now we can, once we've specified that, we can use maximum likelihood estimation because we've specified this complete distribution. And generally speaking, we're not going to have an explicit form. So we do have an explicit form in the case of linear regression, but we don't for most other GLMs. But we can use maximum likelihood estimation and then an algorithm, a numeric algorithm, typically Fisher scoring, to actually get parameter estimates out of the GLM call itself, right? So that's the general sense of what is a GLM. So then we're talking a little bit about exponential families, right? So we said that the random component, yi, had to be assumed to come from an exponential family. So what is an exponential family? Well, to refresh your memory on this, we say that y is an exponential, or is from an exponential family if its density can be written in this form. Okay, so if its density can be written as the exponential of y times theta minus this function b of theta divided by this function a of phi plus an additional term here which does not depend on theta. It can only depend on y and phi. Now, in this case, we call theta the canonical parameter. Oops. Call theta the canonical parameter, and we call phi either the scale or the dispersion parameter. Okay? And phi is taken to be some known parameter almost always, and theta is typically where our interest lies. Now, the reason that we care about exponential families is because they have a nice score function and they have a nice expected information. And in particular, they're such that we get this result where the expected value of y is equal to the derivative of this b function, and the variance of y is equal to a of phi times by the second derivative of that b function. Okay? And so, in particular, this means a couple of things. First, because of the fact that we have this b prime here and this b double prime here, there's this intrinsic relationship between the mean and the variance in exponential families. And this is an incredibly important feature of them. But the other component here is that we sort of get the unique specification of the likelihood of all of the information that we could want sort of through these functions, right? Now, when you combine that with the nice properties of the score and the expected information, which allow us to use that Fisher scoring algorithm, the exponential families sort of serve quite nicely. So I'm assuming that you've all seen these exponential families before, and so I'm not going to go into a tremendous amount of detail, but I would encourage you to sit down and try to figure out why this expectation actually holds. Maybe I'll make a point of actually demonstrating this for you, but I'm sure this is something you've seen in GLM, and I can sort of provide those resources for you if you haven't seen it. But where does this sort of take us in the context here? Well, most of the distributions that we're talking about in general in a statistics course actually happen to be exponential family, right? So what I have listed here is a table which has some common distributions that happen to be exponential families. And then I've provided the link function and the form of the link function. And I'll talk a bit about exactly what that is. But just noting here, first of all, that all of these functions, which are, sort of probably the most common distribution functions that we're going to talk about, happen to fall in the exponential family. So normal, exponential, binomial, Poisson, and tons more that you're familiar with happen to be exponential family. So when we're saying that we need our outcome to be limited to the exponential family, it's actually not a huge sort of limitation on what we're doing, because so many of the distributions that we care about, so many of the distributions that we work with happen to be exponential family anyways. Okay, so what are these link functions that I'm providing right here? Well, these are candidate functions to choose for G, and they're a special kind of candidate function. So if we go down and read what I'm writing in the text down here, these are the canonical links for various exponential functions. So in theory, you can take any link function, but these link functions have the property such that G of mu is equal to theta. Okay, and so what this means is if you clear this and we go back to this density back here, right? Those link functions are all selected such that if you take g of mu, where mu is the expected value of the distribution, so you take g of e of y, then those are going to equal theta, okay? And so this provides us with sort of some very nice properties once we actually work through the calculus. And again, you would have seen this derivation. And when we're using the canonical link, we can use algorithms that are a lot more efficient. We don't have to. You can apply any link to any function. But in this case, these are the canonical links that give us sort of the standard types of regression analyses that we're going to think about. So maybe I'll just point out a couple of examples here. So with the normal distribution, we're saying that the canonical link is the identity link, okay? And so what does this mean? Well, if we go back here, if we are trying to convert this to the normal density, Well, maybe what I'll do is I will pull up my whiteboard here, and we can say that the normal distribution, so f of y, has this density where we would take 1 over the square root of 2 pi sigma squared, and then we take the exponential, and we're going to have negative y minus mu squared over 2 sigma squared, right? And so the question is, how does this correspond to this exponential form that we have on the screen right here? And the idea is going to be that we could expand out this term up here. And so we'll have the exponential of, if we do the binomial expansion here, we have y squared minus 2y mu plus mu squared divided by 2 sigma squared, right? And so here, if we assume that the variance is known, right? So if we take sigma squared to be some known constant, okay, then we can sort of separate this term out into a couple of different situations here. And so to make sure that we're writing it in exactly the same form, what I want to do is then say that this is going to equal, and we will write this as, start with the exponential, right? And we want to take y times theta. So we want our y out front. And if we're thinking about this in terms of a function of y and theta, well, theta here is going to be our mu parameter, or at least it's going to be something related to our mu parameter, right? And so it's this term that we want to write out front. So I'm going to write y times by negative factored into the top here, so 2 mu. Okay, and then I will write the minus, we need some b of theta term, so we're going to have minus mu squared. Divide this all over 2 sigma squared. And then what do we have left? Well, we have this minus y squared over 2 sigma squared term as well. So I'll write that minus y squared over 2 sigma squared. And then we have this constant term out front, and it's constant because we're assuming sigma squared is known, right? And so if we want to put that into the exponential, then we need to write it as the log. So what we can do there is say plus the log of 1 over square root of 2 pi sigma squared. Okay, and so now you're going to see this written in a few different ways, but the general idea is that you can treat this as our theta, but what you'll more commonly see is you can factor this 2 out, and then you're left with just a 1/2 there, right? And by doing it this way, now we have y times theta directly, where theta is mu, and we started this whole discussion by saying that the identity function is the canonical link for the normal distribution. So what that means is that if we take g of mu equals mu, and we apply that to theta in the normal distribution, well, theta in the normal distribution is mu, so g of mu is equal to theta because that equals mu. And so that's probably a little bit confusing there, but the idea is that when you take a canonical link and you've written this out in standard form in the exponential family, you should find that the canonical link applied to the mean of the distribution gives you the canonical parameter, or gives you theta. And in this case, for the normal distribution, that's the identity link. Theta is equal to mu. So hopefully that makes some sense. Hopefully you've seen that all before. But the primary limitation of a GLM is that it needs to be implemented through maximum likelihood estimation, and therefore it requires the specification of the distribution of y, right? So we've specified, we've assumed that it follows some exponential family. We specify that exponential family, and then we work from there. Now, when we saw linear regression, we saw that it wasn't actually necessary to assume normality, right? It was convenient as one way of getting to the answer, but we could also view it as least squares estimation. We can do a similar thing with GLMs, right? So it's not strictly necessary. And so how do we get around the specification of a specific distribution function? Well, we can turn to what is known as quasi-likelihood instead. So instead of specifying the exponential family, we simply specify that the expected value of yi is going to be given by some function applied to our linear predictor here. We specify a variance function, and so that variance function is going to be equal to that scaled dispersion parameter times by our variance function there. So v of mu I is some variance function. And note that they're both functions of the mean here, and that's because we saw that there's this intrinsic link between the mean and the variance, right? So it makes sense to think about them as functions of mu I. And then what we're doing is we define this u function to be equal to the difference between yi and mu I, and then scaled by phi times by our variance function, right? So we've specified a mean, we specified a variance, and now we build out this equation here, which is the difference divided by the variance. This is called the quasi-score function. Now, if we solve this system of equations, which is given by the summation of the partial derivative with respect to beta, times by this quasi-score function here, if we solve that equal to 0, then this gives us a consistent and asymptotically normal estimator for beta. Okay? And so this has let us specify a GLM or a GLM type function without ever actually assuming the distribution. So if we had correctly assumed an exponential family distribution, then the quasi-likelihood function is exactly the likelihood function. However, we got to that point without ever needing a distributional assumption. And so what this means is that by using this quasi-likelihood technique here, we've sort of taken all of the GLM, all of the information about a GLM, and we've expanded that out to be able to not need to assume that it's a GLM. If it happens to follow an exponential family, then the quasi-likelihood method will solve down to be exactly the same thing. But if it's not an exponential family, this is still going to be consistent and asymptotically normal. So in the same way that we could relax the normality assumption with linear regression, we can relax the exponential family or the distributional assumption within GLMs. So if mu I is correctly specified, then beta hat is consistent. If the variance function, so if v of mu I is incorrect, we still can estimate the variance of beta hat. And sorry, I'll clarify this first point here slightly more as well. So when I'm saying whenever mu I is correctly specified, beta hat is consistent, what I mean by that is regardless of whether v of mu I is correct or not, we get consistent estimates. As long as the mean function is correctly specified, as long as that xi beta is correctly specified with respect to the link function, we get beta hat to be consistent. If we've specified the variance function to be correct, then we can obviously estimate the variance correctly. But even if we do not specify the variance correctly, we can still estimate the variance of beta consistently. Okay, so that's a really powerful property. The value of phi can be estimated by using a modified version of the method of moments approach, which is quite useful for us. And it will generally be less efficient than the MLE, but it's more robust, right? So the question is, if we don't need to specify a distributional assumption, why do we learn GLMs, that type of thing? Well, it's more efficient to actually use the maximum likelihood estimate, but in the case that we don't have a good distributional basis for our properties, or in the case that the variance does not sort of look like we might be able to accurately estimate it, well, then we can use this technique and we don't need to specify the variance correctly, and we don't need to specify an explicit distribution, and doing so will still provide consistent estimation as long as we have a large enough sample. Okay, so that's sort of the trade-off we're making. So we get this robustness to misspecification at the cost of needing additional data. So, in summary, GLMs extend the idea of linear regression to other types of outcome. They can be fit using maximum likelihood estimation by assuming an exponential family, specifying a linear predictor, and specifying the corresponding link function. They can also be fit without the need for a distributional assumption by leveraging quasi-likelihood estimation. However, like with linear regression models, GLMs require IID data, okay? And so I've said, oh no, because that was the whole reason that we needed marginal models for continuous outcome data in longitudinal data. Well, we're going to need a similar type of thing in order to analyze longitudinal data that are not continuous. And so that's sort of where we're going to be going next with this. So as always, I hope that this made sense. It was a very quick overview of this. It was all supposed to be a review for you. If any of this is not familiar or doesn't make any sense, please ask me questions and I'm happy to clarify whatever. But if you remember all of this from your GLM course, then you're in a great spot to start applying longitudinal methods to non-continuous data. And that's where we're going to be going in this course next. So thanks for watching, and I will see you in the next lecture video.